This is lesson 7.8, Geometric Sequences. Your objective is to write and use recursive formulas for geometric sequences. A geometric sequence is a number sequence formed by multiplying a term in a sequence by a fixed number to find the next term. An example of a geometric sequence would be 9, 3, 1, 1/3, etc. A geometric sequence with a starting value a and a common ratio r is a sequence of the form a times r, a times r squared, a times r cubed, etc. For the recursive definition, the sequence has two parts. First, you need to identify the initial condition as a sub 1, which is equal to a, your starting value, and you also need the second part, which is the next term, a sub n, equal to a sub n minus 1, the previous term, times r, which is your common ratio, for n greater than or equal to 2, as part of the recursive formula. An explicit definition for this sequence is a single formula. A sub n, or the nth term, is equal to a sub 1, your initial condition, times r to the n minus 1 power for n greater than or equal to 1. Every geometric sequence has a starting value and a common ratio. The starting value and common ratio define a unique geometric sequence. Which of the following are geometric sequences? Here we have 20, 200, 2,000, that should be 20,000, and 200,000. Find the common ratio. Well, you need to multiply by 10 in order to get to the next term. So our common ratio is r equal to 10. Therefore, the sequence is geometric. The next one, 2, 4, 6, 8, 10. There is no common ratio here. To go from 2 to 4, we multiply by 2. From 4 to 6, we have to multiply by 1.5. From 6 to 8, we have to multiply by 1.3 repeating. And from 8 to 10, we have to multiply by 1.25. So this is not a geometric sequence. However, if you recall, this is an arithmetic sequence because all we're doing is adding 2 to get to the next term. 5, negative 5, 5, negative 5, 5. This has a common ratio. We're multiplying by negative 1 to get to the next term. So our common ratio is r equal to negative 1, making this a geometric sequence. Any geometric sequence can be written with both an explicit and recursive formula. The recursive formula is useful for finding the next term in the sequence, and the explicit formula is more convenient when finding the nth term. Find the recursive and explicit formulas for the sequence 7, 21, 63, 189. Identify the starting value. A sub 1 equals 7. Our common ratio, r, is 21 divided by 7, so you're taking the second term divided by the first term, which equals 3. To write our recursive formula, you need to write a sub 1 equals a, our initial starting point, so a sub 1 equals 7, and you also need the second part, which is the next term, a sub n, equal to a sub n minus 1 times our common ratio, which is 3. So you need both of these in order to write the recursive formula. For our explicit formula, we only need to use that one formula. So our a sub 1, which is our initial point, is 7. We're going to substitute that in. Our common ratio is 3. We'll substitute that in for r. So our recursive explicit formula is a sub n equals 7 times 3 to the n minus 1 power. Two managers at a clothing store created sequences to show the original price and the markdown prices of an item. Write a recursive formula and an explicit formula for the sequence. So we have 60, 51, 43.35, $36.85, etc. Our initial point is 60, and our common ratio is 0.85. We take the second term and divide it by the first term. So our recursive formula, you need to identify both parts, your initial point, a sub 1 equals 60, and that a sub n, meaning the next term, is equal to the previous term, a sub n minus 1, times the common ratio, 0.85. Our explicit formula is a sub n, or the nth term that you're looking for, equal to 60, which is the initial point, times 0.85 to the n minus 1 power. You can also represent a sequence by using function notation. This allows you to plot the sequence using the points n and a sub n, where n is the term number and a sub n is the term. A geometric sequence has an initial value of 6 and a common ratio of 2. Write a function to represent the sequence. Graph the function. So using our explicit formula, a sub n, we're going to replace that with f of x. A sub 1 is our initial value, so that's 6 times 2, our common ratio, to the n minus 1 power. So we need to figure out the first few terms. So when x is equal to 2, our value, our output is going to be 12. So that's going to be our term. The second term is going to have a value of 12. When x is equal to 3, so our third term is going to be 24. Fourth term will be 48, and fifth term will be 96. So we're going to plot these points, and we're just going to go by ones here. Whoops. So 1, 2, 3, 4, 5. And here we're going to go by tens. I'm not going to fill everything out. I'm just going to have you use your imagination, and we're going to plot the points. So when our second term is equal to 12, our third term is equal to 24, fourth term is 48, and our fifth term under 100. Whoops. Once you plot your points, you can connect the dots using a nice smooth curve. So let's see if I can do that here for you. This is what happens when you do not have a smartboard. And yours should be a lot prettier than mine. Alright, some sample problems. Which of the following are geometric sequences? If the sequence is not geometric, is it arithmetic? So let's look at 3, 6, 12, 24, and 48. To get from 3 to 6, we multiply by 2. 6 to 12, multiply by 2. 12 to 24. Yes, this is a geometric sequence. And the common ratio is 2. Three to 6, 6 to 9, 9 to 12, 12 to 15. Well, to get from 3 to 6, we multiply by 2. From 6 to 9, we multiply by 1.5. 9 to 12, 1.3 repeating. 12 to 15, 1.25. This is not geometric. And let's just check if it's arithmetic. Well, 3 to 6, we can add 3, plus 3, plus 3. Yep, this is definitely an arithmetic sequence, because there's a common difference of 3. Alright, 4 to 7, 7 to 11. Well, to get from 4 to 7, we need to multiply by 1.75. 11 to 7 to 11, we have to multiply by 1.57. From 11 to 16, we have to multiply by 1.45. So this is not geometric. And let's see if it's arithmetic, though. Well, plus 3, plus 4, plus 5. This is not geometric or arithmetic. Find the recursive and explicit formulas for each sequence. So we have 2, 4, 8, 16. Well, let's see. We have a common ratio of 2. So for our recursive formula, we need to identify, we need the two parts. A sub 1 equals the initial value, which is 2, and that the nth term, or the next term, is equal to the previous term, a sub n minus 1, times the common ratio, which is 2 in this case. For explicit, we're saying that the nth term is equal to the initial value, which in this case is 2, times the common ratio to the n minus 1 power. And what's nice about this one, 2 here is the same base as this one, and this is 2 to the first power, which means I can actually add the exponents. So I'm going to change the color here. I'm going to make that a 1. So I can really rewrite this as 2 to the 1 plus n minus 1 power, which simplifies to 2 to the n. This only works in this case because my initial value and my common ratio are the same number. Let's look at this one. 40, 20, 10, 5. So our recursive, remember I always identify the initial value. So that's 40. And the next term is always determined by the previous term times the common difference, which in this case is 1/2 or 0.5. So our explicit formula will be the nth term, a sub n, is equal to our initial value times our common ratio, 1/2, to the n minus 1 power. And here I can't do this nice simplification because we do not have the same bases.